In this video, we're going to be talking about uniform circular motion. That is, objects that are moving in a perfect circular path. So a simple example of this is me moving this mouse in a circle here, right? So the mouse is moving in a perfect circle, and what we want to do is we want to figure out what requirements is there on an object in order for it to move in a circle, right? Because there are lots of ways that I can move this mouse. I can throw it to the side, right? Or I can throw it upward or downward or any of those things. And most of those do not result in the object moving in a perfect circle. So there must be pretty strict requirements on what it takes for an object to move in a perfect circle. In order to get the simplest possible scenario, what I'd like you to imagine is that I am standing in outer space, far from any planets or anything, so there's no gravity nearby, there's nothing nearby, and I am just spinning the mouse in a circle like this. And what we're going to do is we're going to draw all of the forces on the mouse in this situation where we're far from the Earth. So here I have drawn our mouse, and I have put the velocity of the mouse, so it is spinning kind of in a circle here. And the only force acting on that mouse is the force of tension, right? Because there's no gravity on it. I am not physically touching the mouse. The only thing touching the mouse is the cord, and that cord is a tension force, so it always pulls along the direction of the cord. Okay, so just a little terminology so that we can discuss this more fluidly. Instead of using, say, X and Y, we want to be able to talk about things that point towards the center of motion or things that are perpendicular to that, right? So if I drew the mouse, for example, when it's here, the velocity vector would look like this, and the force of tension would point directly inward again, right? So the mouse would be moving this way, but feeling a force inward. And this is true anywhere. Anywhere that I draw the mouse on its entire path, the force would point inward toward the center of the circle. So we would like to simply be able to talk about that force of tension without having to change and break it up into X and Y components at every point, because the X and Y components of this force of tension here are clearly different than the X and Y components of this force of tension here, even if those two forces have the same magnitude. So what we would like to do is we would like to say, if I have some circle, things that point toward the circle, so arrows like this, we label as radial, and these would be inward because they point in toward the center of my circle. So the force of tension here is radially inward. Likewise, we could have forces, not in this picture, but we could have forces, which are radially outward. That is, they point away from the center of the circle. So all of these other arrows that I'm drawing here would be radially outward lines. Whenever we're using a coordinate system, we would like our two directions to be perpendicular to one another, right? So that X is perpendicular to Y, for example, right? So here we would like another coordinate such that I could move from, say, this point here to a point over here, say, right? If I want to do that, obviously moving directly toward or away from the circle will not help me to move this way. So we need another direction, which is called the tangential. So we need another direction, which we will call the tangential direction. So the tangential direction here looks like this or that. So depending on my relation to the center of my circle, my tangential directions are always perpendicular to the radial direction to the circle at that point, right? So what we see is, if we look back, thinking about this picture in relation to our mouse, we see that our velocity is always tangential, and our tension force, the thing that keeps us moving in a circle, is always radial. Physicists call a force that generates circular motion a centripetal force. This force must be pointing inward, and it must always have a magnitude. The magnitude of the centripetal force, which I indicate with a sub c, is always equal to mv squared over r, where r is the radius of the circle that the object traces out, right? So if I have some ball on a stick or on a string that is moving in some circular path, this is the radius, v is the velocity, and of course m is the mass. So whenever we introduce a new equation, the first thing that we should do is double check that it makes sense in a couple different ways. One, let's check the units. Well, the units of my centripetal force should be the units of mass, kilograms, the units of velocity squared, which is meters squared per second squared, divided by the units of radius, which are meters. So meters cancels that, and I get kilogram meter per second squared, which looks like a Newton, which is of course a unit of force. So the units check out. Now that we've checked the units of our equation, let's see if we can check the intuition of the equation to see if it makes sense physically. So let's imagine that I want you to run in a circle. So you are going to run with some velocity, and I want you to run in a circle. Now, if you're sprinting as fast as you can probably run in a circle that is very large and wide, right? You probably can't run in a really tight circle at the fastest possible speed you can run at, right? So what that tells us is that if I have a very large speed and I want to run in a small circle, that gives me a large numerator from v squared being large, and it gives me a small denominator because the radius is small, right? And again, you can think of this as the radius here. Large number divided by a small number means I need a lot of centripetal force if I want to move very quickly and run in a small circle, which is very difficult to do, which is why, in general, if you're moving very fast, you can only run in a large circle because you only have so much centripetal force that you can generate. You can only push yourself inward to run in a circle so hard, and you just can't generate enough force to run very quickly and run in a small circle, to have a large numerator and a small denominator. Likewise, if I asked you to walk, right, so now you're just walking slowly, you could run or you could walk in a much smaller circle, right? If your velocity is lower, you can afford to have a smaller radius and still generate enough force to turn in the circle. So it makes sense that if I'm walking, I can make a tight circle. If I'm running, I can only make a large circle because I can't generate that much centripetal force. Good. Mass also makes sense if you think about if you were to carry like a 50-pound backpack on your back. having more mass is going to make it more difficult to turn quickly, especially if you're moving fast, right? If you're running as fast as you can with a 50-pound backpack on your back, it's going to be very difficult to turn quickly. You're going to have to make a big circle because your body can only generate so much centripetal force inward, right, in order to turn you. Now let's try using our net force equation on a centripetal force problem. So let's imagine that I'm swinging an object in a vertical circle, so it's moving like this, and I'm on Earth, right? So let's imagine that the object is at the very bottom of its path, moving to the right here. Now, the force that causes us to move in a circle is the radial force. So what we're going to do is we are going to think about the net radial force on the object, which is simply equal to the sum of all of the forces that point in the radial direction, either toward the center of the circle or away. Now in this case, our forces are, of course, the force of tension pointing toward the center of the circle and the force of gravity pointing downward away from the circle. And I'm going to use the convention that any force that points radially inward is negative, and any force that points radially outward is positive. A quick note, this coordinate system actually rotates with my object. So if my object were in this position, my coordinate system would be plus, minus, and if my object were in this position, my coordinate system would be plus, minus. I always define radially inward to be negative and radially outward to be positive, and that rotates along with my object. Good. Notice we also do not care about any forces left or right in this case, because we are only concerned about the centripetal force, and the centripetal force is a radially inward force. Okay. Now, in order to stay moving in a circle, we require that the net radial force equal the centripetal force, mv squared over r. This is our requirement in order to stay moving in a circle. And we can set that equal to just the sum of all of our forces, Fg plus Ft. For uniform circular motion problems, this mv squared over r really takes the place of our ma. So this is, instead of adding up our forces and setting them equal to ma, in this case it would be a radial, we add them all up and set them equal to mv squared over r. In fact, v squared over r is really just your radial acceleration here. So it's really ma, we're just writing it. Acceleration as v squared over r. Okay, so we know that based on my values given here, we can calculate the force of gravity. That force of gravity is going to be positive based on my coordinate system. So the force of gravity for a 2 kilogram object is going to be 19.6 newtons. We don't know what the force of tension is because the force of gravity is trying to pull the object out, and we know that we need more than just to counteract the force of gravity. We actually need my object to curve upward, which means that we would expect the force of tension to be greater than the force of gravity, and we're going to be able to solve for it using our net force equation. Okay, so we know the value of the force of gravity. We know that the centripetal force is mv squared over r, so I can say this is going to be 2 kilograms times 25 meters squared per second squared, all divided by 1 meter, which looks like 50 newtons. So when I look at this equation, I see that 50 newtons, and based in my coordinate system, the centripetal force needs to point radially inward, which is negative. So I have a negative value here for my centripetal force in my coordinate system, equals 19.6 newtons plus the force of tension. So my force of tension equals 69.6 newtons, and it is negative because negative 50 minus 19.6, negative 69.6 newtons. So my force of tension is negative, which tells me that it points radially inward, and it is a larger value than the force of gravity because it not only has to overcome gravity, but it has to accelerate the object upward in order to get it to turn. Now that we've done it at the bottom of its path, let's think about what happens if we put the block at the top of its path up here. So in that case, I will erase this picture here. We can set up the exact same system. Our centripetal force hasn't changed because we are still moving at the same velocity with the same radius with the same mass. So my centripetal force of negative 50 newtons still holds. So my F net in the radial direction is still negative 50 newtons. Now my force of gravity and my force of tension are both pointing downward here. They are both pointing radially inward, which means that they have negative values in my coordinate system. So the force of gravity in this case is negative 19.6 newtons. And setting up my F net radial equation, negative 50 newtons, negative 19.6 newtons, plus my force of tension. So my force of tension is 30.4 newtons. Negative. Now in this case, what happened is that my force of gravity is actually helping. It is acting in the proper direction to be a centripetal force. Whereas when the mass was at the bottom, the force of gravity was trying to stop it from moving in a circle. Now it's actually helping. So I need less tension at the top than I do at the bottom. If you try to swing a heavy mass in a circle, you'll actually notice this. Partially, if you are trying to swing a heavy mass in a circle, part of it will be this effect where gravity is actually helping you and takes less tension. And part of it is because you'll probably have the mass moving slower at the top than it is at the bottom. And when you move more slowly, it takes less centripetal force. So if you took a really heavy object like a bowling ball and tried to swing it in a circle, it would be very, very difficult to keep it moving at the same velocity at the top as it is at the bottom. So not a fantastic experiment, but it's one that you can try at home, and you will notice that you need less tension at the top of your path than you do at the bottom.